In this section, we're going to be taking a look at some different forms of proofs. So the two that I want to look at are called direct and indirect proofs. So let's take a look at a direct proof. And before we do that, the direct proof is going to involve two definitions. These are going to be very basic definitions that hopefully you're all familiar with already. Definition one is two angles are congruent if and only if they have equal measures. And definition two says that a right angle is an angle having measure 90 degrees. So hopefully you're all familiar with these two definitions. Okay, now what are we going to prove? So the given is that angle A and angle B are right angles, right? And from that given hypothesis, we want to prove that angle A is congruent to angle B. So in this semester, in this class, we're going to be working both with two-column proofs and also paragraph-style proofs. So I generally prefer paragraph-style proofs. I'm more comfortable with them. I do them all the time. I never do two-column proofs. But I do know that two-column proofs are still pretty popular in high schools, and so we're going to do both, and I want you to come out of this class with having a better idea of what the pros and cons of both forms of proofs are. And for this example of a direct proof, I want to look at a two-column proof of this. So on the left column, we're going to have our conclusions, and on the right column, we're going to have our justifications. This is the proof. This is what the proof looks like. There are three conclusions and justifications for each of them. So we start with our given that angle A and angle B are right angles, and then our first conclusion from that is that the measures of angle A and angle B are 90 degrees. And this is just from the definition of a right angle. So we're just using definition 2 here. Okay, so we're justifying this first conclusion with definition 2, definition of a right angle, and also from our given. And then our second conclusion, after we have conclusion 1, then we can, since angle A and angle B are both 90 degrees, then we can conclude that those angles are equal. And that's just some basic algebra. It's an algebra fact that if x is 90 and y is 90, then x and y are equal. And then our final conclusion is that therefore, that's what those triple dots mean, is therefore, angle A is congruent to angle B. And that was definition 1. That's the definition of congruence, right? Definition 1 said angles are congruent if they have equal measures. Okay, so we could sum this two-column up. This might be like an oversimplification, but we could still sum it up as follows. If we know the statements P implies Q and Q implies R are both true, then we can conclude that P implies R. So P implies Q implies R, right? P implies R. All right, how is that appearing in this proof? What is P, what is Q, what is R? Well, we're trying to prove that if angle A and angle B are right angles, then angle A is congruent to angle B. So this should be our, this is going to be our P, and this is actually going to be our R, and then our Q should be like the middleman here. So I would say that Q, a good interpretation of what the middleman here is that angle A and angle B are equal. Right? So angle A and angle B are right angles implies Q that angle A and angle B are equal, which implies that statement angle A is congruent to angle B. This right here, final conclusion. Okay. So we could sum this up with just a couple of if-then statements. So anyway, a direct proof of a statement P implies Q assumes the hypothesis P, and then uses known facts and definitions to conclude that Q is true. And that's exactly what happened up in our previous example, our previous proof. We assumed the hypothesis and then used known facts and definitions to come to our conclusion, right? We assumed angle A and angle B are right angles, and then we used the definition of a right angle, definition of congruence, and some basic algebra. That would be like our other basic facts to get to our conclusion. So anyway, that's what a direct proof is. So now what is an indirect proof? So an indirect proof, sometimes called proof by contradiction. These are slightly different, but regardless. An indirect proof of P implies Q assumes, or you could think of it as like pretending that Q is false and finds a contradiction somewhere. And commonly you will find the contradiction by showing that P is false. So you assume P is true, and it's, so the way that I think of it is like, it's like proof by sarcasm. It's like, all right, well, if we're going to assume Q, excuse me, if we're going to assume P, and we want to prove that Q is true. Well, what if Q is not true? Well, if Q were not true, sarcasm, then like that would mean that the sky is green or something. You would find some contradiction somewhere in your logic if you were to assume that P is true and Q is false, right? Commonly, people will the contradiction that they'll find is like, all right, what if P is true and Q is false? Well, the contradiction that they would find is that P is actually false. So they don't actually use the fact that P is true in their reasoning. So what they're actually doing is they're assuming that not Q is true. They're assuming that Q is false, which means that not Q is true. And then they're actually following some train of thought to show that not P is true. So P is false, not P is true. Negation of P is true. And you might recognize that this is the contrapositive of P implies Q. And so so this is fine. So some would argue that this is technically a direct proof because it's a direct proof of the contrapositive. You're just showing that you're providing a direct proof that not Q implies not P, which, here it's just like a matter of pedantics or just however you want to like describe it. But anyway, sometimes indirect proofs and proof by contradictions and proof of the contrapositive, these things all get conflated. It doesn't really matter. Just know that these are all techniques that you could do to prove things here. Don't get hung up on like, what is an indirect proof? What is a direct proof? It doesn't really matter. It's just know that these are all different things that you can do. So here's an example of an indirect proof. I don't know why I said another example. Well, it's another example of a proof, but this one's going to be an indirect proof. All right, so this Proposition 9 from Euclid's famous book called Elements. So this is the book where I think it was a series of books or whatever, but point is he proved a bunch of things about basic geometry. This is where he built up his axiomatic system for geometry and started proving a bunch of things from it. So in this book, Proposition 9, he shows that in any triangle, the greater angle is subtended by the greater side. I'll show you a picture of what this actually means in a second. But before I do that and before I get into the proof, I also want to say this is going to use Proposition 18 comes right before this one. Proposition 18 says that if one side of a triangle is larger than a second, then the angle opposite, the bigger side, is going to be larger than the angle opposite the smaller side. So here's a let me bring this up actually so that I can talk about this. Yeah, so proposition 19 says that in any triangle, the greater angle is subtended by the greater side. So, so it's saying, so here in this picture, angle B is bigger than angle C, and proposition 19 says that since angle B is bigger, then the side AC has to be bigger than the side AB. Okay. Subtended just means like that's the side that is opposite that angle. Okay. So anyway, let me put that back down there and get into the proof. All right, any triangle. So all right, so let's assume that angle B is bigger than angle C. So I'm going to do this in paragraph style. All right, angle B is greater than angle C. So we want to show, I'm abbreviating want to show as WTS. I'll probably do that a lot this semester. We want to show that what? Well, what I just said was that the theorem stated that the side AC compared to the side length AB, AB should be smaller than AC. So AC should be bigger. Okay, so that's what we want to show. So off the top of my head, I don't know how to do this directly, but we can use proposition 18 in a clever way, as well as some facts about isosceles triangles, and also an indirect proof here. So there are three cases for what could happen. We could have that AC is in fact bigger than AB, in which case we are done. We could have that these side lengths are actually equal. Or you could have that AC is in fact smaller than AB. Okay. So let's do the second one first. So I'm gonna just like get rid of this for now, and then we'll just write it down later. So if AC equals AB, then we actually have an isosceles triangle here. So if we have an isosceles triangle, let me draw an isosceles triangle. Great, this is barely isosceles. Okay, whatever. Pretend it's isosceles. No, I just want it to be better. That's better. Okay. All right. So here's our angle B. Here's our angle C. Here's A. So if we have an isosceles triangle, then that would actually imply that angle B is equal to angle C. And Euclid actually proves this fact earlier in that book. So this is a fact that he already proves before. So that's why we're allowed to use this fact, is because he actually proved it. He went through and proved it already. Okay. So this is a contradiction though, because we already assumed that angle B is greater than angle C. therefore they cannot be equal. Whenever I find a contradiction in a proof, I like to do this symbol. Some people like to do this symbol where it's like two arrows pointing at each other. Both of these are fine. The one that I draw, it's supposed to be like two swords are clashing. It's just the one that I like. Do whatever one you like. Okay, so anyway, that's our contradiction there. So this is not a possibility. So AC cannot be equal to AB. All right, and then our last possibility was AC is less than AB. So if this is true, then what can we do? Well, we can use his proposition 18, which says that if one side of a triangle is larger than a second, then the angle opposite the first is larger than the angle opposite the second. So let me bring this triangle down again. Okay, so if AC is less than AB, then that proposition actually tells us that angle B must be less than angle C. Which is another contradiction. So I'll put the swords clashing to signify that this is a contradiction. So the only possibility left is the thing that we're trying to show, which is that AC is greater than AB. And with that, we are done. So I'll put the box, which I fill in at the end to signify that we're at the end of the proof. Okay, cool. So this is an example of what is called the method of exhaustion, or the rule of elimination, which says the following. So the rule of elimination says the following. So it says that if R, S, T, is a complete finite set of logical possibilities. So like in our proof, like this complete set of logical possibilities was that like number one was equal to number two, number one was bigger than number two, and number one was smaller than number two. So A is equal to B, A is greater than B, or A is less than B. That is a complete finite set of logical possibilities in the example that we were doing. But maybe you have like 5 possibilities or something like that. So if you have this finite set of logical possibilities such that at least one of them implies a statement Q, which you're trying to prove, and all of the other possibilities imply that P is false, then P implies Q is a valid statement. It is a true statement. So for us, what we did was we said that our complete set of logical possibilities was, those side lengths are equal, or one is bigger, one is smaller. And then two of them implied that our original statement was false, right? Both of them implied that our original statement, which was that angle B is greater than angle C, and both of our contradictions were that like, angle B was actually bigger than angle C. The contradiction was that angle B is equal to angle C, which is impossible because angle B is assumed to be greater than angle C. And then in our other one, then we show that angle B was less than angle C, which would imply that our original thing was false. And then the only other logical possibility implied, well, it actually was that our conclusion was true. So this is just like a general generalization of what that proof was trying to do. And this is a sort of thing that like used to get used like all the time, and is just a very common proof technique. All right, so I think I will end it there.